Hello. So I'd like to discuss an alternative path for galactic bulge evolution involving the central black hole. The galaxies and the central black holes co-evolve over cosmic time, as suggested by observations of the scaling relations, such as the black hole mass-bulge mass relation. And these observational correlations only concern the spheroidal component of galaxies, that is, the galactic bulge, while there seems to be little or no connection with the disk component. Now, as the energy released by the accreting black hole is much larger than the binding energy of the galactic bulge, the resulting AGN feedback can have a major impact on galaxy evolution. Now, in most galaxy evolutionary scenarios, AGN feedback is required to quench star formation in galaxies, so either by removing or heating the ambient gas, eventually leading to red-ended ellipticals. Now, this is a standard negative feedback paradigm, which has been implemented in various numerical simulations. However, feedback from the central black hole may also play other roles in galaxy evolution. So in this perspective, we explore the possibility of black holes triggering star formation in galaxies inside the AGN feedback-driven outflows. So we consider radiation pressure on dust as the driving mechanism. So AGN radiation pressure sweeps up the surrounding dusty gas into an outflowing shell that propagates on galactic scales. Now, the squeezing and compression of the outflowing gas may trigger star formation within the galactic outflow itself. So we parameterize the star formation rate in the outflow as this. And for typical parameters, we obtain star formation rates of 10 to 100 solar masses per year. Now, provided that the initial speed is lower than the local escape velocity, the newly formed stars remain bound to the galaxy. Thus, the formation of new stars in the galactic outflow can lead to a significant increase in the galaxy's size. So in this picture, new stars are formed at increasingly larger radii in the AGN feedback-driven outflow and gradually build up the outer regions of the galaxy. Now, such AGN feedback-triggered star formation in quasi-spherical outflows mainly contributes to the spheroidal component of galaxies, the galactic bulges and ellipticals. Now, the radial extent of the stellar envelope depends on the radial extent reached by the AGN outflow, which depends on the central black hole mass. So the corresponding radii can range from a kiloparsec to tens of kiloparsecs, comparable to the typical size of the central bulge in these galaxies and the whole bulge in elliptical galaxies. The most massive black holes would then be associated with giant ellipticals, while smaller black holes may be linked with the inner bulge of disk galaxies. Now, we expect such AGN feedback-driven star formation to be most effective at high redshifts, so when AGN activity was more important, around cosmic noon. Now, this particular form of galaxy growth can be directly compared with the so-called inside-out growth of massive galaxies observed over cosmic time. Now, of course, galaxies cannot grow forever, and we can define a critical radius where the outflow becomes transparent to the central radiation. So beyond this point, radiation pressure on dust is no longer able to drive the galactic outflow. This critical radius may define a sort of physical boundary which sets an upper limit to the characteristic size of galaxies. Now we note that the enclosed mass here is equal to the galaxy mass obtained by assuming the effective Eddington limit for dust. In fact, the ratio of bulge mass to black hole mass tends towards this characteristic value, which is quite close to the observed mass ratio. Now, in this framework, we also predict a simple relation between characteristic radius and mass of this form. And interestingly, this is quite similar to the size-mass relation observed in early dark galaxies. Therefore, the global scaling relations followed by the spheroidal component of galaxies could be essentially set by AGN radiative dusty feedback. Now, until recently, the idea of AGN feedback triggering star formation in galaxies was just an hypothesis, since there was no empirical evidence for such positive feedback. But the situation has changed in the last few years. So the discovery of star formation inside the galactic outflow has now been observationally confirmed, with the first direct detection obtained for a nearby source. So basically, spectroscopic analysis of emission lines indicate that the outflowing gas must be photoionized by in situ star formation within the galactic outflow itself. Now, more recently, star formation inside galactic outflows has been further observed in a larger sample of local galaxies, so suggesting that the phenomenon could be rather common and perhaps even more prominent at higher redshifts. Now, AGN feedback-driven star formation may be considered as a new form of positive feedback, which should complement the standard negative feedback paradigm. In fact, the coevolution between galaxies and black holes may involve both forms of AGN feedback, and so is likely to be much more complex than previously thought. Now, another element complicating the coevolution picture is the discovery of ultramassive black holes in compact galaxies. So these are extremely massive black holes with mass up to 10 to the 10 solar masses, residing in very small galaxies with a typical size of 1 kiloparsec. The prototype is NGC 1277 in the Perseus cluster, which has an unusually large black hole to bulge mass ratio, so making it a major outlier in the local scaling relations. It has been suggested that these peculiar objects might represent relic galaxies that somehow survived without change since their formation at high redshifts till the present day. Now, perhaps the most intriguing aspect is the connection between the presence of an ultramassive black hole at the center and the compactness of the host galaxy. So we investigate the possibility of a direct link between the two via extreme feedback at early times in the context of our AGN feedback scenario. So we suggest that at high redshifts, extreme feedback from the ultramassive black hole blows away all the gas beyond a kiloparsec or so, while triggering star formation at inner radii in the galactic outflow. Since the gas reservoir is removed at early times, the formation of new stars is prevented at later times, so that only a compact stellar bulge is left behind. Now, some of the outflowing stars may escape the galaxy and form a diffuse stellar halo around the compact remnant, possibly becoming part of the intergalactic stellar population or even intracluster light. Now, on the other hand, less massive black holes drive less extreme feedback, such that the stars formed in the feedback-driven outflow remain bound to the galaxy and contribute to its size and morphological evolution. So following the episode of star formation triggering in the galactic outflow, radiation pressure will sweep away the remaining gas and dust. Now, the dusty gas ejected by radiative feedback may then propagate on larger scales and contribute to the metal enrichment of the surrounding circumgalactic medium. So we have seen that AGN feedback-driven outflows may play important roles in setting the co-evolutionary path. Now, moreover, the observed energetics of galactic outflows, and in particular, the large momentum flux and high kinetic powers, can be quantitatively accounted for by radiative dusty feedback. Now, in reality, AGN feedback is a direct consequence of black hole accretion, and the central black hole spin can have macroscopic effects on the host galaxy. So the black hole spin determines the radiation pattern emerging from the inner accretion disk, which in turn determines the geometry of the radiation-driven outflows on galactic scales. So here we show the black hole spin-induced radiation pattern in the form of polar diagrams. So in the case of a low black hole spin on the left, we see that the radiation pattern is vertically focused, so giving rise to polar or prolate outflows. Whereas in the case of high black hole spins on the right, the radiation pattern is much more isotropic, so leading to quasi-spherical or oblate outflows. The black hole spin can actually shape the large-scale morphology of galactic outflows. Now, reversing the argument, we can potentially deduce the spin of the central black hole from the observed morphology of galactic outflows. So in our picture, black holes are responsible for both triggering star formation in galactic outflows, the positive feedback, as well as eventually clearing the dusty gas out of galaxies, the negative feedback. So the central black hole may play a dual role in shaping the structural and morphological evolution of galaxies across cosmic time. Now, to try to answer the question, unexpectedly, black holes may actively contribute to the buildup of galactic bulges via positive feedback. Thank you.